Hi, so this is a quick tutorial about what we've been doing the last couple of days. Today's January 13th, Wednesday. So Tuesday and Wednesday talking about sample means and sample proportions and what their distributions look like. So let me just go through here real quick what we did in class yesterday. And I'm going to start with that Fathom demonstration. Okay? The way we started it was we said, okay, we're going to generate, or take a sample, of 100 women, and we're going to measure their heights. Okay, now I know that the average height of the population, okay, so let me just make a note here, the average height of the population of women is 64.5 inches. Okay, now normally that's something we're not going to know. We're not going to know the population parameter, but just work with me here. Let's pretend like we know it. This represents a sample of 100 women. See 100 down here. Okay? What we're going to do is take these 100 women, we're going to find the average of their heights, and we're going to drop that average into this box. Then we're going to take another sample of 100 women, find their average, and drop it in the box. So this box here is going to have a collection of the sample means of each of our samples. And you can see that happen when I click the button. Each of the dots that goes across represents a sample mean. And this table here is collecting the sample means. And this graph down here is graphing the sample means that we're collecting. So we're going to get to 35 and it's going to stop. And this is the dot plot that represents the data of, or represents our sample means from our 35 samples. Okay, now this doesn't really look like much. What we can do is this. I'm going to turn animation off, and I'm just going to keep accumulating the cases. So instead of doing 35 one at a time, I'm going to do 300 all at once, and I'm going to add them to the 35 that are already there. So we're going to get 335 samples and 335 sample means, and this is the dot plot. And look at that, it's looking more normal now, isn't it? And I can keep doing this, and as I do it, you see how this graph is looking more and more normal. Okay? Now you notice how it kind of goes up and down and up and down and up and down and up. So it's not really that smooth, okay? But it does have that normal-ish shape to it. The other thing to notice is look at the low number and the high number. Okay? And what I'm going to do right here is put 63.6 out to about 65.3. That's the range of the sample means that we have right now. Okay, so then the next thing I did in class was I said, all right, let's assume that we don't have 100. Let's assume our sample size is really going to be 400. So what I want to do is add 300 more women to my sample. So you notice how now my sample size is 400, not 100. Okay, so what I'll do is clear this table out, and I'm going to start collecting measures again. Okay, there's 300, there's 600, there's 900, there's 1200. Okay, now you notice we still have a normal shape. You notice how the gaps, how we had the, the up, down, up, down, up, down stuff, we don't have that as much anymore. Okay, and you notice how our range goes from 64 on up to about 64.9. So our range is actually less than it was before. And that's illustrating how the statistic, the sample mean statistic, gets more precise when the sample size gets larger. Okay? What this says is this shows me the relative probabilities of getting sample means for each of these numbers. And then what we saw in class is that X bar has a normal distribution with a mean of the population mean and a standard deviation of the population standard deviation over the sample size. And we just showed that as n increases, this standard deviation, the spread of the distribution, will decrease. And we saw that in this example here. So that's what I did in class yesterday, and that was what we were showing. Okay, this is basically called the central limit theorem. And that one homework problem probably threw you because it said use the central limit theorem, but I never told you what it was. Of course, you could have looked in the book, but that may have been asking a little bit too much. Ha ha, right? So now you know the central limit theorem is what tells us that x bar becomes normal as n gets larger. Okay, we'll talk about p hat in a second because p hat has basically the same idea. Okay, so now we're back. The next thing we need to talk about is what we discussed today, the conditions and assumptions. Okay, here's the situation with that. We notice that the normal distribution gets better the higher sample size gets. Well, that means the reverse is true too. If the sample size were to decrease, the normal approximation would get less, and we would not have a normal distribution if the sample size is too small. So one of the things we have to do whenever we look at this x bar being normal is we have to look at the conditions and the assumptions that will tell us x bar is normally distributed. And what I said in class today is that we have two choices. Our first choice, 1a, I'll do that again. Our first choice, 1a, says that if the population is normal, then x bar will also be normal. It doesn't matter what the sample size is at all. If the population is normal, x bar will be normal too. That means then I already wrote it, so I'll take that out. If that doesn't work, meaning we don't know if the population is normal, so if population is not normal, or we don't know, then sample size n has to be big enough. And big enough for us right now is going to be greater than or equal to 40. Okay? We'll quantify that and we'll make it a little bit more specific later on. What you put in the assumptions is just how you answer it. Okay, so for the women example, on the Fathom example we just had, if we were looking at x bar and trying to find, let's say, the probability of finding a sample mean of women's heights of being greater than 65 inches, we would have to first show that x bar was normally distributed. Okay? The way we could do that would be with this choice, the first one. Since we know heights are normally distributed, we could write this down. If the population is normal, then x bar will also be normal. We would say yes, population of heights is normal. So basically the assumption side is what proves the condition. Now most of the time we'll be able to actually show something in the problem that will prove it. Every once in a while, however, we'll have to assume that that is true, and we'll talk more about that next week when we get to that. Okay, so let's go ahead and summarize. We have conditions and assumptions for x bar. If the conditions are true, then x bar has a normal distribution with a mean of mu, standard deviation of sigma over square root of n. Okay, now let's talk about what happens with p hat. Let me make sure my time is okay. Oh, I'm going to have to stop this. We'll continue on the next, we'll do part 2.